Okay, so today we're going to be going over two sections today. The first one being 2.5, linear functions and models. I'm going to just briefly touch on linear functions. It's a short section to begin with, but also if you need extra help, then you can email me, and I do have a section on linear functions in my college algebra playlist, so go check out the college algebra playlist, look for linear functions, and then you can help yourself to all the extra knowledge that you want. So linear functions, recall that a linear function is a function of the form f of x is equal to ax plus b. So in the expression defining a linear function, the variable occurs to the first power only, so we only have a first degree polynomial. We can also express a linear function in equation form as y is equal to ax plus b. From section 1.3, we know that the graph of this equation is a line with slope a and y-intercept b. Obviously, yes, you can look at the college algebra playlist, but yeah, I guess we did go over it in here as well. Forgot about that. Okay. And then we see our our definition basically just rewrites what we read above. And we're just going to hand wave this one a little bit. So example 1, determine whether the given function is linear. If the function is linear, express the function in the form f of x equal to x plus b. Linear functions are first degree polynomials. So we're just going to snip all this because, again, we're just talking about it. Can I do current page? No. Okay, so let's take that back. Okay, so all you have to do is check to see if we, create a first degree polynomial or not, right? A, is always first degree, so it's linear. This is first degree, it's linear. This one would be a second degree polynomial because when we distribute this x through, we notice we have, 4x and then plus a 3x squared. The 3x squared makes it no longer a linear equation, but a quadratic equation. And then, of course, D we can rewrite also into linear form. So only C is not a linear equation. The rest of the section would be graphing linear equations. Again, things that we have seen before. Slopes and rates of change. Okay, this is actually important. I mean, they're all important, right? But you'll see why I'm trying to scoot past this section quickly, because the next one is a doozy. So slope and rate of change. If we let f of x equal to ax plus b be a linear function, then we know that having x1 and x2 being two different values for x, and if y sub 1 is equal to f of x sub 1, so basically saying if we plug in that first value of x, we get a y1. So the subscripts match. See here. Then we have the points x1, y1. This is basically point 1. Okay, so x sub 1, y sub 1 means the x and y values of the first point. And we have x sub 2, y sub 2. These are the values of the second point. So it lie on the graph of f. From the definition of the slope and average rate of change, we see that we have this, the change in y over the change in x. Certainly we did go over this. Yeah, I mean, maybe section 1.3, and again, that will be on the YouTube playlist. So what I'm going to start doing now is in eLearn, I'm not going to be giving you, each individual lecture. I'm just gonna paste the playlist. So if you need to go back and look at stuff, it's easier to navigate. And of course, the latest lecture will be the latest video. But anyways, from section 1.3, we know that the slope of a linear function is the same between any 2 points. Nothing much there. Of course, we have a rate of change. This is nothing new for any of us here. I guess I will snip this. Okay, and I believe the rest of the examples in this section just pertain to just a little some word problems to really get you acclimated to linear equations. Okay, but again, linear equations is something that you've seen quite often in your mathematical journey. Next up, you might not be familiar with, Or if you are, then you have forgotten about it. Guaranteed. So, transformation of functions. What does that mean? So transformation. So if you transform something, what do? You change it, right? So earlier in this chapter, it might have been section 1, I talked about parent functions, right? I told you guys you need to memorize these parent functions. You need to memorize what x squared looks like. You need to memorize what x cubed looks like, so on and so forth. This is why. We're going to be able to look at these functions, look at those parent functions. We'll actually just look at functions in general, and then be able to determine what the parent function is, and then from there determine how to transform that function. And we can graph. We'll be able to graph these in our head within like 3 seconds, right? Or at least have a rough idea of what these functions look like when you graph them. Let's snip this. I think this is good. Alright, so in this section we study how certain transformations of a function affect its graph. This will give us a better understanding of how to graph functions. The transformations that we study are shifting, reflecting, and stretching. So let's start with the easiest, vertical shifting. So vertical shifting. Adding a constant to a function shifts its graph vertically. Vertically upward if the constant is positive, and downward if it is negative. In general, suppose we know that the graph of y is equal to f of x. How do we obtain from this graph? How do we obtain from it the graphs of y is equal to f of x plus c and y is equal to f of x minus c, where our c is a value greater than 0. So it can be confusing, I guess. But this is basically saying, any values that are greater than 0. So, we'll just use integers here. 1, 2, 3, 4, right? Well, we'll skip the 2, don't want 1, 2, 3, 4. So it'd be essentially saying, f of x minus 1, f of x minus 2, f of x minus 3. Whereas if we just let, this is actually dumb. I don't know. I mean, it can be a very rigorous definition for those of you going into mathematics. But for now, I feel like that's confusing to you. So the y-coordinate of each point on the graph of y is equal to f of x plus c is c units above the y-coordinate. So if we add some sort of number to the function, then we go up on the y-axis. And if we subtract some number, then we go down. So let's see what an example of that looks like. I feel like examples are a lot better. I think this is actually good. I think this gives a better idea of what we're trying to say here. So let's move this over here. Do we have space? Not too much space, huh? All right, let's fix this. Okay. All right, so that this picture over here really kind of drives home the point. So suppose we have some value c that's greater than 0. Okay, so basically just any integer that's greater than 0. Okay, so if we wanted to graph y is equal to some parent function plus c, okay, the parent function in this picture here would be the blue line. Okay, so this is my parent function, and if I add some c value, if it's just the parent function plus some constant, then notice how we go. We shift that blue line up to turn into that red line. Okay, we make a vertical shift up c amount of units. Whereas if we subtract some constant, if we have the parent function, again this blue line, this parent function, and we subtract some constant, then notice how we would shift down c amount of units. Okay. So let's look at an example. I'm going to just snip this, and we're just going to kind of, we're going to talk about this out loud, and then I'll paste the solution and what the graph actually looks like. Okay, so a, what's the parent function in a? Well, obviously it would be x squared, right? So it's going to look like, so we're going to do just a rough graph here, and then I'll paste in a more precise graph here in a moment. So I know that the parent function would be x squared. So it's going to look something like this. Okay. Well, if I were to make A be red and B be blue, okay. Well, red is x squared, my parent function. Okay. The white graph over to the right, the white graph to the right. I would shift it up 3 units. So I would go, 1, 2, 3, and then it would look something like this. Okay. And then the blue line would be, -2. So, I would go 1, 2, and then I would shift it down 2 units. Okay. Now, real quick, how do I know what point to shift? Well, the way I always do it is I use the point 0, 0. So imagine if I have some, point right here. All right, well, I would take that and I can move it up, down, left, right, wherever I wanted to, depending on what sort of transformation I need to make. So, for instance, in the first one, I needed to shift up 3 units. So I just moved this landmark up 3 units, and I graphed it as such. And same for the blue line. I took that landmark, again, the landmark for all of these parent functions. I'm pretty sure, let's make sure. Yeah, until we get to logarithms, and exponential functions, the landmark for all of these parent functions that we went over in section 1 are going to be 0, 0. Again, so you take that point and you just take this origin point and move it around depending upon the transformation. So let's look at more of a precise graph here. So let's see, what do we read here? Yeah, nothing different than what I would said. So, and honestly, I feel like my graph wasn't too bad, was it? Okay, so we see that the blue line here is my original function, x squared, and then the red line would be that function shifted up 3 units, and then that purple line would be that function shifted down 2 units. And that's vertical shifts. Horizontal shifts. All right, so horizontal shifts. Okay, so horizontal shifting. Suppose that we know the graph of y is equal to f of x. How do we use it to obtain the graphs y is equal to f of x plus c? So it would be y of x plus c. So it's essentially, we have it as y is equal to f of x, okay? But this is now saying f of x plus c. So we're essentially putting a constant in there that we are adding to, okay? And then likewise down here we are subtracting. So we do vertical shifts, okay, so previous slide, vertical shifts if we add or subtract to the parent function, okay? That needs to be written down. Vertical shifts are if we add or subtract to the parent function. Horizontal shifts are if we add or subtract to the variable, okay? So for instance, a vertical shift, so we're going to do vertical shift, okay, of, f of x, and let's do x squared. X squared would be, going up 2 units. That would be a vertical shift, right? I am adding 2 to my parent function being x squared. Now, x squared is an example we use, and you know what? Let's just go ahead and change the x squared since we used x squared on the previous slide. Let's do the square root of x. Okay. So that's a that's a vertical shift. We add to the parent function. A horizontal shift would be if we add or subtract to the variable. So this would be, the square root of x minus 5. Okay, that would be a horizontal shift. Notice how I'm adding or subtracting to the variable. The vertical shift is to the parent function. The horizontal shift is to the variable. Okay, now we know that depending on the sign of this, we go up or down. If we're adding a constant, we go up. If we're subtracting a constant, we go down. Horizontal shift is the exact opposite of what you think it would be, right? So this is x minus 5. So if we look at a plane, you might think, hey, we're going to the left 5 units, okay? But we're not, right? It's going to be the opposite essentially, right? So if it's an x minus 5, that means we're going to be shifting to the right 5 units, okay? And if that's not intuitive to you, and it probably might not be, right? Because it's not as easy as negative left, positive right. Well, that's because if you recall, if we have some x minus 5. Actually, let's do this. Let's not put the parentheses there. We have x minus 5 is equal to 0, right? Well, what's x equal to? X is equal to a positive 5 again, which is the opposite sign of what we're attaching that x to. Okay, so that's how we solve our equations with the zero product principle, right? And that's what we're doing here. So hopefully it becomes a little bit more intuitive to you why if we are subtracting from the variable, then we go to the right, and if we were adding to the variable, we go to the left. Because if you were to again set this equal to 0, you would see that. So what else? All right, so looking down at down here. So we've got, it's basically saying everything I just said, but with letters, right? If we have f of x minus c, okay, so some parent function and we're subtracting c. Okay, this blue line would be the parent function. Then we would shift to the right c amount of units. Okay, so for my example up here, we would have shifted to the right 5 units. That's the c. Here, it's just some arbitrary number, some c units. Okay. And if we wanted to graph y is equal to f of x plus c, then we're going to be shifting left c amount of units. So again, the blue line is my parent function in this particular example. And we're going backwards. We're shifting left c units. So if we do subtraction to the right, addition to the left. Okay. So let's say an example. All right, so I'm just going to go ahead and snip the graph and show you instead of drawing it. But we will talk about it. So this first one, what's a thick line? Okay, so here we go. The first one. All right, we know my parent function is x squared, so it's going to be some x squared. It's going to look like that, right? Okay, so but it's a plus 4. So that plus 4 tells me we're going to be going to the left 4 units. And sure enough, that's what we see here. Okay, the blue parabola there is my parent function x squared. This red one is us taking that parent function and shifting to the left 4 units. Okay. Likewise, if we were to look at the next example, the parent function again is x squared. So again, the parent function is the exact same, the parabola. Okay, but it's an x minus 2, so that means we're going to be shifting to the right 2 units. Okay, and again, the shifting part comes from that landmark I told you about, the landmark being my origin, right? So I've taken this point at the origin, and then I would have shifted to the left 4 units, and then for B, I would have shifted to the right 2 units. Okay, so you take that landmark, that 0, 0 landmark, and you shift it up, down, left, right. Okay. Combining them, so if we combine these two transformations that we just talked about, how would we go about doing that? Okay, well, it doesn't actually say it in the textbook. I don't think it does anyways. Let's see. Yeah. Okay, so there is a procedure to go about which transformation you do first, which transformation you do second, which transformation you do third. And we're going to be talking about a lot of transformations today, okay? But just remember this. The very first keep on getting those thick numbers, huh? The very first transformation you need to do every single time, the very first one, will need to be a horizontal shift. Okay? That's the very first one you do. The second one doesn't really matter. Okay? But as long as the last one, the last transformation you do, is a vertical shift. Now again, I left that 2 blank because I mean it could be 2, 3. You could do three different transformations before you get to the last one. But my point here is this: first is always the horizontal shift. The last is always the vertical shift. And honestly, let's have a little bit of consistency here, right? And we'll put this. We'll just write first here. Okay. So the first transformation is always horizontal. The last is always vertical. Doesn't matter what the middle is. Okay. It kind of does, but for the sake of this, not so much. I promise you'll be just fine with that. So with this one, if I am to do the horizontal shift first, okay, well I will take this graph. So what's my parent function here? My parent function that is not all right, little minute movements it doesn't like, right? So my parent function is what? My parent function is the square root of x. Okay, so if my parent function is square root of x, I know that if I graphed it, right? My parent function, if you recall, and again, you're supposed to memorize these parent functions, would look like this. Okay, that's what my parent function looks like. It is just simply the square root function. So I said the first thing I do is a horizontal shift. So what is my horizontal shift? Okay, well it looks like my first thing I'm doing here is I'm going to be shifting to the right. Oh, that is a thin line. I forgot. Okay, let's make it the medium line. Okay, so oh yeah, first thing I do is a horizontal shift. That horizontal shift would be to the right 3 units, and then lastly, what I would do is I would go up 4 units. Okay, so if I'm shifting to the right 3 units, and something like this, 1, 2, 3, like that, and then we would shift up 4 units, so it'd be something like this: 1, 2, 3. Actually, let's put it on the actual axis, huh? 1, 2, 3, 4. So I mean, of course, my graph isn't really that great, so I'm just gonna go ahead and snip this. I don't know if I can slip all that. So will that fit? Yeah, that'll fit. Okay. So their graph is obviously a lot more precise than mine, and what I should have done, I guess, was focus in on just the first quadrant. But there it is. We take this graph and we shifted it to the right 3 units, and then we shifted it up 4 units, and then this red line is what the graph of the square root of x minus 3 plus 4 is. Okay, so maybe a week ago, if you looked at this, you would have to, if you graphed it, you would have to make the XY table there, whatever value you plug in and you get the Y value out, right? But this time, all right, we're in pre-calculus now. We're going to be able to look at a function and be able to determine what it looks like, right? And one moment. Alrighty. So that's example 3. Finish up horizontal shifting. Okay. So more transformations we have. We're talking about reflection. Okay, so if we're talking about reflection, all right, I mean, obviously it's not a abundantly difficult concept to grasp, right? We know what reflections are. So suppose we know the graph. Suppose we know the graph of y is equal to f of x. How do we use it to obtain the graph of y is equal to negative f of x and y is equal to f of negative x? Okay, so in this equation, we're taking the negative of a function. And in this equation, we're taking the negative of the variable. So the y-coordinate of each point on the graph of y is equal to negative f of x is simply the negative of the y-coordinate of the corresponding point on the graph of y is equal to f of x. Whew. So the desired graph is a reflection of the graph y is equal to f of x in the x-axis. On the other hand, the value of y is equal to f of negative x at the x is the same as the value of y is equal to f of x at negative x. So all this, I'm gonna tell you right now. I know that's going in one ear and out the other for you. Okay. Here's what you want to know. You want to know the actual meat of this, and we'll see it here. Reflecting graphs. So if we have y is equal to negative f of x, okay, negative of the parent function, then we're going to be reflected about the x-axis. Okay, so let's think about this. If we have, well, let's do this. Let's actually write f of x. F of x is equal to let's have our parent. No, that's not the parent function. Let's do f of the negative square root of x. Okay, well, this is the negative of the square root function, obviously. All right, and we did on the previous page a square root function. Looks like that if we graph it. Kind of more like that, but whatever. Well, we're taking the negative of that parent function, so we're going to take it and it's going to be flipped across the x-axis. So instead of looking like this, we reflect it across the x-axis and it's going to look like this. Okay. Likewise, if we were to take, likewise probably ain't even the right word there, is it? If we were to take the negative of the variable, okay, then we would flip it across the y-axis, and that's what this is saying. Okay, we take f of the negative of the variable, then we flip it across the y-axis. And that's it. So if it's a negative of the function, we reflect it across the x-axis. If it is the negative of the variable, we flip it across the y-axis. So let's get into an example. And once again, I should probably just have copy that whole thing, huh? So solution, yeah. Okay, so looking at A, what's my parent function? Okay, well, it's an x squared, and that's my parent function, x squared, and we know it's a parabola that opens upward. Okay, well, if I take the negative of that parent function, then we take it and we flip it down. That's it. All right, and B, what's my parent function? Well, it is the square root function, which, again, if I graphed it, looks like this. And actually, I did give you that example on the previous slide. Sorry about that. It's an accident. But anyways, you see it more precisely there. If I took the negative of the variable, then I would take that graph and I would flip it across the y-axis. So again, the negative of the function is flipped across the x-axis, and the negative of the variable is flipped across the y-axis. Okay, so far we have vertical shifts, horizontal shifts, and then we have reflection across the x, or I'm sorry, reflection about the x and reflection about the y. Those are 4 transformations that we have so far. Let's look at some more. this is where it starts to get a little more tedious. And it becomes more open to interpretation, I guess. That's actually not the best thing to say about this, but we'll roll with it for now. Okay, so suppose we know the graph of y is equal to f of x. How do we use it to obtain the graph of y is equal to c, all right, some number times the parent function, okay? So for the vertical shift, we noticed that we multiplied the function, we added or subtracted to the function some number, okay? So, excuse me. Vertical shift, we added or subtracted some number, and then we went up or down the y-axis, right? Well, if we're going to multiply the parent function by something, then we're going to be talking about vertical stretching and vertical shrinking. Okay. So if we were to take, so we're looking at this right here, c some constant times some function. If our value is greater than 1, then we're going to stretch the graph vertically. Okay, so for instance, let's look at again this blue line is my parent function. Okay, just a little wave. Well, if I were to take that function and I multiply it by some c, then imagine what we're doing is we're taking that blue line and we're just stretching it vertically, right? We're just taking it and stretching it vertically to create that red line. That's a vertical stretch. Okay. Well, if my c is between 0 and 1, so basically if it's a fraction, right? A fraction, a decimal, anything like that, then we're going to be doing, what we're going to be doing is we're going to be making a vertical shrink. So imagine taking this blue line, again, the blue line would be the parent function. Imagine taking that blue line and then vertically shrinking it, okay? So instead of stretching it, we're going to be shrinking it. So again, we take that blue line and then we basically essentially go the opposite way. We just kind of flatten it vertically. Okay? So again, we have a vertical, let's go back and actually do that. Look at it. Vertical shifts are when I add or subtract to the parent function. Vertical stretches will be multiplying by the parent function by some number. Okay, so that there is a lot of consistency there, and then of course we'll see horizontal stretching being similar to the horizontal shifting. But anyways, let's look at some examples here. So looking at this, looking at A, okay, my parent function is obviously x squared. It tells us that, but you don't have to be told. You can just essentially see that we have an x squared there. So this is my parent function. Okay. Well, the number in front of my parent function is a number greater than 1. Okay. And so since it's greater than 1, that means we're going to be stretching it. So let's draw a graph out here, or a plane. And then we're going to draw the graph of x squared. Let's actually put that in white. So again, x squared is my parabola, okay? Well, if I were to stretch it by a factor of 3, and this is where when I said open to interpretation, but I kind of backtracked on that because I don't want anything in mathematics to be, at least this mathematics, to be open to interpretation. But the reason why is because, for stretching by a factor of 3, we don't really know what a factor of 3 is, right? Do we? How do we know this is a factor of 3, and this isn't? Okay, we don't, right? But obviously, if you did your XY table, you can make it precise. But this isn't so much about precision as it is about knowing what these graphs look like. So, for instance, this would be a good example of stretching by a factor of 3, right? I'm taking that graph x squared and I'm pulling it. Okay, I'm pulling it and stretching it by that factor of 3. All right. Well, b, that is a fraction in front of my parent function. So what I'll be doing is I'll essentially going to be shrinking it or flattening it, right? So it's the white line, again, the white line is my x squared. So imagine if I took that and then I just flattened it out. It looks something like this. Okay. So let's see, I probably should have done it on the previous pages too, huh? Maybe not so much, it's not a big deal. But I will denote x squared, 3x squared, and 1/3 x squared. Oh, real quick, before I forget. So these definitions, this is for our c greater than 1. This is for our c between 0 and 1. Okay, so let's examine what happens at 1 and then what happens at less than 0, okay? Well, if c is equal to 1, well, then it's just a parent function, isn't it? Because it'd be, x squared and then 1 times x squared, well, that's just a parent function. Okay, well, what if it was less than 0? Well, then it would be, a negative whatever number, right? And then that means we would flip it across the x-axis, and then that 3 there would tell us that we would stretch it. Okay. Oh yeah, I wanted to give you the good graph. So I graphed the not so good one, then I snipped the good one, like so. So that is a vertical stretch. Okay, so combining, so we'll do this one. No, wrong thing. No, whatever, that gave me time because I want to do the whole thing anyways. Okay, so I said the first thing that we're going to do every single time, okay, first is always horizontal shift. So looking at this graph, looking at that, this tells me the first thing I'm doing is I'm going to be shifting to the right 3 units. Okay, so if this black line is my parent function here, you see it? The first thing I'm doing is shifting to the right 3 units, okay, which would be this purple line. So that's essentially the first step. Okay, so let's actually, maybe we can put a first here. First step. All right. I see that we're going to have to do a vertical shift as well, though, right? Because I'm essentially adding 1 to the parent function, okay? But vertical shifts we do last, so we're not going to touch that right now. Looks like we're going to be doing a reflection, okay? Because it is a negative out front. Then what we're going to do is we're going to shift this across the x-axis. Let's see, I'm going to erase that. So we would shift this across the x-axis, so we would get this blue line, okay? And it's simultaneously stretching it by a factor of 2. So this down here, the blue line would be second. Let's put that down here. Second, okay? So real quick, the first step was our horizontal shift to the right. That's first step every single time. If you have a horizontal shift, you do it. The second step, we combined them here, was a flip across the x-axis because it was a negative of the parent function. Okay, right here, a negative of the parent function, but also that 2 tells me we're going to be vertically stretching it by a factor of 2. So notice how it is just a little more, stretched than my parent function there. Okay, and then the last thing I'm going to do is I'm going to shift up 1 unit because that of this one right here. Okay, so that red line would be third. And that's not a good R, is it? R. There we go. Third. And that's it. So if I were to tell you, last week, if I said, what does this graph look like? Some among you that might have, remembered college algebra might be like, oh, okay, so that's a shift to the right 3. We're going to be flipping across the x-axis, stretching, and then we're moving up 1. So this might take maybe 10 seconds of some visual or of some mental visualization there, right? To think your way through what it actually looks like. But now we know what these functions look like when we graph them. Okay, through vertical vertical shifts, horizontal shifts, reflections, and vertical stretching. Okay. Now, obviously, if we have a vertical stretch, we're going to need to have a horizontal stretch, don't we? So remember how we had horizontal oh shoot, I forgot the word. Shifts. You know, right? It's a hard word to forget. Horizontal shifts were based upon, you know, what we added or subtracted to the parent function. Okay, I'm sorry, to the variable. Same thing can be said here. This is what we're going to be multiplying the variable by. Okay, good. Okay, so it reads, now we consider horizontal shrinking and stretching of graphs. And again, actually, I'm not even going to read this up here because I feel like that does get a little confusing for many of you. A lot of you just want to know this. Okay. Now, again, if you're going into mathematics or something, this is a very rigorous idea behind it. But I know many of you care about this, so we're not even going to read that, but you can. So this reads, to graph y is equal to f times c of x. Okay, the function of x, okay, f of x, but we're multiplying it by some value of c. Okay. So if c is greater than 1, okay, remember on the vertical stretching, if we had c is greater than 1, we stretched. And if c was between 0 and 1, we shrunk. It's going to be the exact opposite. So instead of it stretching for greater than 1, we're going to be shrinking it. And if c is between 0 and 1, we're going to be stretching it. Okay, just the exact opposite of vertical stretches and shrinks. So horizontally, let's see. Okay, so this blue line would be my parent function, whatever it is. And if I have a value c that's greater than 1, then I shrink the graph by a factor of 1 over c. Okay, so notice how we take this graph and we horizontally shrink it. All right, so we're essentially, you know, it's like clapping your hands, right? We're shrinking it. All right, now for the stretch, you know, essentially do the opposite motion. Instead of clapping together, pull out, and that's what we see here. We're essentially pulling the horizontal the graph horizontally away from each other. Again, the blue line is my parent function. The red is us stretching that parent function. Okay, let's. Okay, so to graph y is equal to f of x, the graph is shown in figure 8. We see it down here. Sketch the graph of each function. So a, y is equal to f times, or f of 2 times x. Okay, so that 2 times x, that c value, okay, the constant there, is greater than 1. Okay, so what we're going to be doing is we're going to be taking that parent function, this parent function, and we're just going to horizontally squish it, okay, or shrink it. So this graph is taking the parent function and then just, you know, clapping it together. Right. Well, next up, b, y is equal to f of 1/2 times x. So that means we're taking that function, this function, and we're doing the opposite of clapping. Okay, so instead of clapping it together, we're stretching it out, and you see how we stretch it out there. Okay. So what do we went over? We went over vertical shifts, horizontal shifts, reflections about the x and y axis. We went over vertical stretching and shrinking and horizontal stretching and shrinking. These are all transformations that you do to a function to graph it. Okay, so you wouldn't really again, some among you may remember this, and this might just be nothing new to you, but for the others, being able to look at a function and kind of graph it in your head and get an idea of what it looks like is what we're focusing on now. Okay. Next up, even and odd functions. Yeah, let's read this. Okay, so if a function f satisfies f of negative x is equal to f of x. Okay, so meaning if I replace the x value with a negative x and I get back my original function for every x in this domain, then we call that an even function. Okay, so for instance, we have f of x equal to x squared. Okay, if we replace that x with a negative x, so instead of saying f of x, we say f of negative x. We replaced that x with a negative x. We did the arithmetic, and we got back the original function being x squared. Then we say that it is an even function. Okay. And an even function, if you recall, is a function that is reflective about the y-axis. Next up, let's look at, oh, no, that's not what I want to do. There we go. Let's look at this. If we plug in a negative x and we get the negative of the function back, negative of the parent function back, then we call that an odd function. Okay, and an odd function is not symmetric about the x-axis, right? It would be symmetric about what we call the origin. Okay. And we'll snip that. Put that over here. Okay. All right. So again, what we read earlier, if we plug in a negative x, and notice how it's a negative x for both of them, right? We're just going to substitute in some negative x value. If we get back the original function, we call that an even function. An even function, you see here, is reflective about the y-axis, right? So if I were to take this and I reflected about the y-axis, it would be the exact same thing. And then if I take that negative x and I get the negative of the function, negative of the parent function, then it is an odd function. Okay, and an odd function is symmetric about what we call the origin. Okay, let's do a different color. Let's do maybe green would be good. The origin here. Okay, and the origin is just basically flipped across the y-axis and then flipped across the x-axis. Okay, so we have reflection across the y and then a reflection across the origin. Why do we not have a reflection across the x-axis for it to be an odd function, right? So if an even function is across the y-axis, why is it not the x-axis for odd? Well, think about it, right? So if we have, I have our plane here. If we have a function, okay, and let's just look like this, and then reflected across the x-axis, it's no longer a function, is it? Right? Because we obviously don't pass that vertical line test. Okay, can be an equation, but is not a function, and we're talking about functions here. Okay, so even is reflected across the x, odd is reflected across the origin. Okay. So I told you before, I like to view things, three ways mathematically. So I like to view things, algebraically, and of course that's with our our numbers here. Graphically, and that's what we see here, graphically, and then intuitively, but I don't think there's too much intuition here, right? But let's look at this algebraically. Okay, so if I were to start off with this, and you'll have plenty of these exercises, so new page. Okay, I could graph these, and then I would be looking at it graphically, correct? But instead, what I'm going to do this algebraically. Okay, I'm going to do this with pen and paper and figure it out. So what I'm going to do is I'm going to follow along with what the definition said on the previous page, that if I plug in a negative x, depending on what I get back, will tell me if it's an even function or an odd function, or the last option, neither. Okay, so A. Let's put A up here. A. So I'm going to make this f of negative x. All right, and so that would be, I'm going to plug in a negative x, and that's raised to the 5th power, plus a negative x. Okay, well, what's negative x to the 5th power? Well, that's going to just be negative x to the 5th power. All right, plus a negative x, so it's going to be a minus x. Okay, so I'm going to ask myself, looking at this function here, is it the exact same as this function? Well, no, right? This one is negative x to the 5th, and this one's a positive x. This one's a negative x, and this one's a positive x, right? Okay. Oh well, I guess that leads us into our second question: is it the negative of a? Well, yeah, it sure is, right? Because everywhere where you see a positive here, you see a negative here. So it is the exact negative of a. So therefore, a would be an odd function. Okay. What about b? So I replace the x with a negative x. So I've got that, and then 1 minus, and then it's going to be negative x to the 4th power. Okay, well that becomes 1, and then minus. What is negative x to the 4th power? Okay, well negative x to the 4th power would be x to the 4th, and then it just becomes 1 minus x to the 4th. Okay, so again, we're going to ask ourselves, is this the exact same as this? Well, that was easy. Yeah, it is. Okay, it's the exact same. So therefore, b is an even function. Okay, and then c, we're going to replace the x with a negative x. So h of negative x is equal to, and then we've got 2 times negative x minus negative x quantity squared. So this becomes, okay, so 2 times the negative x becomes a negative 2x. Okay. And then negative x quantity squared is just a positive x squared, but then we account for that negative there, so it just becomes a minus x squared. Okay, so let's ask ourselves, is this the same as, well, I probably could have picked a better color there, huh? Is this the same as this? Okay, no, there's just one slight difference, and there's a negative here, and there's not a negative there. Okay, so it's not the same. Is it the exact negative of it, right? So I've got a positive 2. This is a negative 2. That's good. I have a negative x squared, but this is also negative x squared. Okay, so it's not the exact negative of it either. So it's neither the exact same nor the exact negative. Okay, so therefore we would say that this is neither. Neither. Okay. So those are even and odd functions. Obviously, this would be looking at it graphically. I'm sorry, algebraically. And if you graphed it, you can see that they would, A would be symmetric about the origin, B would be symmetric about the y-axis, and C wouldn't be symmetric anywhere. Let's see if they have those graphs. They do. Okay. So let's see. Do I have room? Not really. So we'll just look at these. So A, we see that it is indeed symmetric about, so I'm looking right here. It is indeed symmetric about the origin. Okay. B does indeed look like it's symmetric about the y-axis. And C, notice how it's not symmetric about anything because we're running through the origin here, but over here is a lot more, right? We're above the x-axis. So it's easy to tell how C is not is neither even nor odd. Okay. And that concludes the lecture.